So we're going to try to see if this works, if I can assemble together slides from different sources. Wish me luck. So we're in this world of what we're going to call partial molar quantities. So let me do my best to explain. If you have properties of a one-component system, extensive properties are the ones that depend only on the amount of the system present. Let's say volume. So if you have a gallon of water or a thimbleful of water, that amount is dependent on how much you have. It's kind of a circular argument, maybe more appropriate for a philosophy class, but I think you know what I mean by extensive properties. Now, on the other hand, molar volume is an intensive property. Whoops, didn't have my drawing tool correctly chosen. So for water again, a mole of water is 18 milliliters or 0.018 liters, no matter how much you have. If you have the gallon of water or the thimbleful, the molar volume is going to be the same. Now this is what's strange. If you add a mole of water to a large sample of ethanol, the new volume is only 16 milliliters more than it would be if you added it to a large sample of water. You're thinking, how can that possibly be? Well, first let's kind of demonstrate what we mean here graphically. If you take a look at this figure, you can see on the far left, so the y-axis is representing the volume. If you are starting on the far left of the x-axis, you could see that you have 0 mole fraction of ethanol. So in other words, pure water. If you had 1 mole of pure water, the volume would be 18 milliliters or 0.018 liters. On the far right hand of this graph, you have pure ethanol. 1 mole of ethanol is going to have a molar volume of around, it says 58 milliliters. Now the middle part is the interesting part. If you just had a half a mole of ethanol and a half a mole of water, you would assume you would just add the molar volumes divided by 2. So it would be 9 milliliters plus 29 to give us 38. So you might expect a value right there to be what the volume of the solution would be. But in the reddish-orange here, you see that the actual real solution has a volume that's smaller than what is being called an ideal solution. Our interpretation of this has to do with how the molecules pack with each other. If you have the forces of attraction between the water and the ethanol are greater, in other words, they form closer interactions with each other than the pure solvent does individually, then you would expect the real solution to end up having a more compacted volume. And so that's what we have below this straight line. So in a mathematical form, what we're going to say is that the volume of the solution is going to be dependent on how much of each component you have. So what we're saying is that the volume of this mixture is going to essentially be the sum of the contribution from the two components. So that's what these two terms are. The first term is this relationship between the volume and component 1 times the amount of N that's added. The change in the volume overall, based on any addition of component 2, is its sort of rate of change. You could think of that in the parentheses times how much you add. Or in other words, this is the volume version of the partial molar volume due to component 1 times its amount added, plus the partial molar volume due to component 2 times its amount added. That would be if there was a change. For an absolute amount, you're just saying that the total volume V is going to be however much you have of component 1 times its partial molar volume, plus however amount you have of component 2 times its partial molar volume, or its contribution to the whole in this particular mixture. So again, what we're saying with this equation is that the total volume of a mixture is going to be the sum of two components, the contribution from component 1 plus the contribution from component 2. Each of those contributions is going to be dependent on how much of each you have and its partial molar volume, or in other words, the amount toward the total that that component will contribute at that particular state. So what we have here is a way to kind of suggest how to measure these partial molar volumes. How do you get a value, V1 bar or V2 bar? So consider a solution composed of substances 1 and 2. To measure the partial molar volume of 2, we're going to have a fixed amount of component 1. Okay, so let's say, I'm just going to make up a number, 50 moles of water. What this curve is representing is what's the new volume when you add, let's say, a mole of component 2, or 2 moles of component 2, or 3 moles of component 2. Essentially what you have is you're developing this curve by pouring in an amount of component 2 into your fixed amount of component 1. What the fact that this function is showing a curve means is that that contribution is going to change at different compositions. So at a particular composition, though, let's say this composition, the partial molar volume at that composition is the slope of the line, again, at that point. So getting the partial molar volume for component 1 at this composition would be pretty straightforward, because you would know the total volume of the solution at this composition, and so you could rearrange the equation above to get partial molar volume of component 1, again, at this composition. Now, the very fact that this line is curved means that the partial molar volume is going to be different at different compositions. I think you could see that this would be a lot of work in the lab to do. However, it can be done, and what you end up getting is the figure on the next slide. So as I mentioned, if one proceeds using the technique from the previous slide, a graph such as this one shown here can be constructive. Whenever the partial molar volume of one component rises, the other component falls. This relationship is true for all partial molar quantities. Note the different vertical scales for water on the left side of this y-axis and for the ethanol on the right. So this graph could end up helping you know what the final volume of the solution is going to be if you know its composition. So let's say you had a 0.5 mole fraction of ethanol, 0.5 mole fraction of water. What that would mean, since this is the line for the ethanol, a 0.5 molar solution would mean, I'm just going to do a ballpark here, about 57.5 milliliters per mole for the ethanol. And the water contribution to the mixture is going to be, I'm just going to say, about 17 milliliters per mole of water. So for a 50-50 mixture, if you had 1 mole of each, the total volume would be the 57.5 plus 17. And I get 74.5 mils for that. So I encourage you to carefully read section 6.3. The derivation of what I'm going to talk to you about right now is there. And it really is kind of a neat connection to something you've seen before. So we're in this world of studying solutions right now, and the fact that solutions even exist means they have to follow the laws of thermodynamics, meaning they tend toward the things you've learned about. They tend toward lower Gibbs free energy. They tend to maximum entropy. So as was true when the concepts were first introduced, the gas phase is a good place to start because it allows us to delay any complexity that comes along with intermolecular forces. So what the derivation on page 218 and 219 does is it takes an expression that we had used for the Gibbs energy of an ideal gas. And so as you see the G bar representing the molar Gibbs energy under the standard state with the naught, and then you could make an adjustment. Higher pressures are going to have more Gibbs energy. Lower pressures than 1 bar are going to have less than standard Gibbs energy per mole. Now if you have a mixture of ideal gases, each component is going to contribute an amount to the total. And so the chemical potential of gas number 1, or gas I, is going to be whatever its contribution is in the standard state to any higher or lower pressure. So there's a parallel there. Now what the derivation leads you to is an equation that you actually saw in chapter 4, that the delta G of mixing is going to be dependent on the fractional abundance of each of those gases. And the same thing with the entropy. Interestingly, you don't get any enthalpy changes upon mixing because these are ideal gases. They're not reacting in any way, and so it's as if they're not even there. Again, not surprisingly, you're going to have the absolute most disorder when you have 0.5 mole fraction of gas 1 and 0.5 mole fraction of gas 2. In other words, the most possible mixture, the most energetically favorable mixture is when you have equal amounts of the two components. So that's what essentially the graph is showing you. You have the absolute lowest Gibbs free energy when you have a mole fraction of 0.5 of each component, and you have the absolute maximum, disorder or entropy when you have 0.5 mole fraction. This is kind of an interesting little thought experiment in which we're asked to consider reversing the process from a two-component solution of equal mole fractions. Basically, imagine unmixing a perfect mixture, which would lead to an increase in Gibbs energy and a decrease in the entropy in the system. That's not favorable. You're going to have to put in energy to kind of go against the curve. Essentially, you're going to have to go the opposite direction. You're going to have to go to higher Gibbs energy as you essentially separate the mixture. Note that the solution becomes progressively richer in one component. What I mean by that is, make sure that I have my pen ready here. As I try to, let's say, make my mixture more pure in component 1, I'm making it less disordered. And so those two arrows kind of contribute to changing the mixture to something that's more pure. But remember what chemical potential is. It's the change in G with the change in component. So notice how the curve gets a lot steeper as you get closer and closer to purity. This means you need to add much more energy to separating components as the mixture, I'll put in quotes, as the mixture becomes more pure. As you can see, there's an implication there. For example, in environmental cleanup or in the purification of compounds. And think about why that is.